Yes, Ayush. Yes, today final mock third. Yes. Let me start. Basic introduce yourself.
Yes, yes, sir. Myself, Ayush Aher. I had done my 10th from PVSS Sainiki School, Loni, and my 12th from SHGM College, Kopargaon. So both of these were affiliated to the Maharashtra State Board. After that, I had done my BSc from Savitribai Phule Pune University. Uh, I had done my BSc from SHGM College, affiliated to the Savitribai Phule Pune University. And after that, I had done my MSc from Dr. B.R. Ambedkar, National Institute of Technology.
Yes, good. Let's move on chemistry topics. Yes, no. NMR,
Yes,
yes. What the main application of NMR and uses in real
NMR
life?
का नहीं था सर मेरे साथ, NMR का चैप्टर नहीं था सर मेरा अभी, सर मेरा कोऑर्डिनेशन और रिएक्शन मैकेनिज्म बचता है.
यस, कोऑर्डिनेशन एंड रिएक्शन मैकेनिज्म. यस, रिएक्शन मैकेनिज्म पे आते हैं. आपके टॉपिक 5 है: ओएमसी, रिएक्शन मैकेनिज्म, कोऑर्डिनेशन, केमिकल बॉन्डिंग और सॉलिड स्टेट. यस ना.
यस, यस, यस,
या नेक्स्ट मूव ऑन
यस,
रिएक्शन मैकेनिज्म. व्हाट द मेन एप्लीकेशन ऑफ रिएक्शन
यस
मैकेनिज्म? 5-10 पॉइंट.
sir. The reaction mechanism means the detailed flow of electron from the reactant to that of the product. So here the reaction mechanism basically have the lot of applications here. So with the help of the reaction mechanism here, uh, we can for example, in the drug synthesis, the reaction mechanism has a lot of importance. For designing any new drug, basically, we have to firstly draw its mechanism, and we have to firstly know that how the product will go further. And another application of the reaction mechanism is that we can predict that which type of byproducts will be formed, whether these byproducts are harmful or not harmful. That we can also see with the help of the mechanism help us in monitoring the different type of uh, the different type of the reaction conditions. So the reaction mechanism will also help us that which catalyst should be used and which catalyst should not be used. So this detailed idea that we will get through the reaction mechanism, and which type of intermediate the will be formed, that idea also we will get from the reaction mechanism basically.
Yes, what the uses of reaction mechanism in real life?
Yes, yes, sir.
5-10 point.
So the uses of reaction, yes, yes, sir. So the uses of the reaction mechanism, so there are the lot of the uses of the reaction mechanism basically. So for example, if you talk about the real life, so basically the formation of the nylon double six basically. So it is formed from the Beckman rearrangement basically. So we get the nylon double six, so which is used in the various, which is used as a plastic and which is used in the various activities by the human beings. The various reactions are going on in our body, as our body is made up of the chemicals basically. So various chemical reactions are going in our body. Uh, so like the intestinal juice that we secrete. So the reaction mechanism has the lot of uses in the living system also.
Any drawback or limitation of reaction mechanism?
Yes, sir, basically, drawing the theoretical reaction mechanism has a lot of advantages. What we can say that the limitations basically, because for the particular reaction we can draw more than 2 or 3 types of mechanism. So that and even now only the lot of reactions are there whose reaction mechanism are not confirmed whether they are going through this mechanism or not. We are not moving that. And for some reactions, there are more than 2 or 3 reaction mechanisms are involved. So basically this is the drawback of the reaction mechanism, theoretical reaction mechanism.
Yes, what's the difference between addition, elimination, substitution, rearrangement reaction? What is the difference?
Yes. Yes. So there are basically the 4 types of the reaction mechanism. So first one, if you talk about, that is addition, elimination, and substitution.
Yes.
So if you talk about the difference, basically, so in addition here, the 2 different groups attach to the saturated carbon atom, unsaturated carbon atom here. For example, here we are having the unsaturated system and we are having here the bromine molecule. So here it get attached here. The 2 atoms are attached on the adjacent carbon atom. So it is basically the addition reaction basically. So the addition basically is the 2 types, that is the electrophilic addition and the nucleophilic addition. But the elimination reaction basically here, the 2 different molecules eliminate from the adjacent carbon atom in case of the elimination reaction basically. So here in case of elimination reaction, here are also the 3 types of elimination reaction, E1, E2 and E1CB basically. So but the difference between addition and elimination is that in 2 groups basically adds on the unsaturated carbon atom, adjacent unsaturated carbon atom. But in case of the elimination reaction, basically here the 2 groups from the adjacent carbon atom leaves basically. For example, if we take the example here, as here it is the leaving group, that is iodine basically, for example, and here is CH3, CH3. So here we are having the strong base basically. So it will remove the proton from here, and so this leaving group will leave firstly, and after that it will remove the proton from here, so that we get the elimination product like this, which is like C is equals to CH2, CH3, CH3. So means 2 groups has been removed from here. And in case of the substitution, basically here the 1 group substitute the another group basically, or we can say that the highly nucleophilic group substitute the good leaving group basically in case of substitution. And here in case of substitution, we have the 3 types of substitution reaction, that is the SN1, SN2 and SNI reaction, sir. So basically, if I conclude in the one sentence, the difference is that in addition we add the 2 different molecules on the unsaturated system. In case of elimination, we eliminate the 2 different atoms from the adjacent carbon atom, and in case of substitution reaction, here we substitute the 1 group with the another group basically, which is highly nucleophilic group, substitute the another group which is a good leaving group basically.
Yes. Any limitation and drawback of addition, substitution, elimination, rearrangement reaction?
Yes. So basically, if you talk about the limitation of the elimination here, so here in case of elimination, basically here is a competition between E1 versus SN1, E2 versus SN2. So sometimes it gets difficult for us whether to predict that the reaction is going through E1 elimination or SN1, or whether it is going through E2, or whether it is going through SN2 basically. An addition reaction here. So these are the limitation of the elimination and the substitution basically, because here E1 and SN1 have a race among both them, and E2 and SN2 have the race among both of them. I think addition reaction is not having that much drawback, but in case of addition reaction, basically if you increase the temperature, sometimes we get the 1,4 product, and at the low temperature basically sometimes we get the 1,2 product basically, in case of the diconjugated system basically. So if you talk about more about the limitation of the elimination and the substitution, here I take one example basically. So here for example for the system which is I take here E1 E2 C CH3 CH3 CH3, and here is the good living group basically. Here is OH basically. I have taken OH here basically. So here we are having the H plus here. We are having here the acidic condition. So we protonate here from here. So here some probability of elimination is there, as this H will leave to form the elimination product. But here, as firstly the water molecule leaves, sorry, this is not for example, here is a CH3, here is basically iodine basically, and if we take any of the O minus basically here, so here what happens basically, the two types of products are formed here basically. So CH3, as firstly the carbocation intermediate will be formed. So this base basically have the two chances, that whether to attack on this carbocation or to remove this proton. So the two different products are formed here basically. So this will be formed in the different yield basically. So this is the limitation of the elimination and the substitution basically.
Yes, what is the function of NGP group?
Yes, NGP.
NGP, Hoffman, SubodhCheM, explain.
Yes. So basically, firstly, if you talk about the NGP, which is the neighboring group participation basically. So in case of NGP, so it is basically the neighboring group participation. So here basically we get the retention of configuration, because here we get the two inversions basically. As we get the two inversions, which leads to ultimately to the retention. For example, if we take the example basically of the NGP basically, here we are having AG group basically, which is C double bond OH here. So here if we add, here is bromine basically, if we add here AG plus here basically and base basically, which is for example if we add NaOH here, so this AG will insert into this bond uh, and this bond and this group get converted into the good living group basically, and this NaOH will remove this proton basically, and here the neighboring group effect will be like this here, and it will get removed from here. So we will form the intermediate like this. So we will have the intermediate like this, and now our OH minus, so here it will attack from the dash basically. So our OH minus will attack from here. So here we will get the retention in configuration basically in case of NGP. Now talking about the SETZEP and the Hoffman product basically. So the SETZEP product basically we get that is the more substituted product, is the major product basically. So it is basically the SETZEP product, and in lot of the cases we get the SETZEP product only. Now talking about the Hoffman product basically. So the Hoffman product, here the less substituted product we get as a major product basically. So in case of the Hoffman product, basically our leaving group is a bulky and which carries the positive charge, so that we get the less substituted products. So I'm taking here one example, that is CH3, CH2, CH2, and H3, NH3 plus basically here, and here we are having CH3. Basically, what happens here, as we know that this leaving group has a positive charge, so it will have the positive charge on it, and here our hydrogen is here, base will take hydrogen from here basically. So here negative type of charge is on this. Basically the negative charge basically on it. So here the intermediate is such that here the carbon atom carries the negative charge. So the primary carbon atom will be more stable as compared to the secondary here, because the negative charge on the secondary carbon will get more destabilized because of the uh, 2 plus I inductive effect. So here is only plus 1 plus inductive effect, so that we get the less substituted as the major product basically in case of the Hofmann elimination. So the Hofmann elimination is seen basically if our base is very bulky or our substrate is basically very bulky. At that time, we get the Hofmann product as a major product basically. And the SubodhCheM product is basically the more substituted product that we get as a major product, where our substrate is not that much bulky, and also the base is also having some small size basically. But in most of the cases, the SubodhCheM product is more favored. Yes.
Yes, Hoffman and SubodhCheM. Any drawback?
Yes, yes. So drawback, yes, sir. Sometimes, sir, the mixture of the two products is formed basically, SubodhCheM and Hofmann product. So one will be the major product and another one will be present in the small quantity also. But the separation of these two products become more difficult basically, because it takes a lot of efforts to separate that another product, because these both the products will have the different properties for which we have made them. So basically the separation is the major drawback, because the 100% product, we will not get any product that is 100%. At least we will get at least one product that is the Hofmann product. So the separation I think is more difficult or the challenging or the limitations, sir.
Yes, good. Next is what the difference between resonance effect, inductive effect, Bijomere effect, and hyperconjugation. Difference
Yes, yes, yes.
in uses.
Yes, yes. Firstly, if you talk about inductive, hyperconjugation, mesomeric, uh, and the resonance. So here the inductive effect is basically of the two type, that is minus I inductive effect or the plus I inductive effect. So the minus I inductive effect is basically shown by the electron donating group, which stabilize that carbocation basically. For example, here we are having any this carbocation like structure. So it is basically stabilized by the inductive effect of 3 plus I groups basically. So it is basically the plus I inductive effect. And here if we have the CF3 groups basically on the carbanion basically, so it will stabilize. Uh, so here this 3 minus I effect basically stabilizes this carbanion basically. So because this uh, this negative charge is basically adjusted or neutralized by this 3 CF, CF3. So the stability of uh, intermediate increases here. And also in case of hyperconjugation basically, so 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 here we can see that. So I'm taking the same case here, which is this case here. So CH3, CH3 and CH3. So basically here the p orbital is unhybridized orbital, which is vacant here. So here the p orbital is vacant here. So here what happens, this hydrogen atom basically goes outside, and here it forms bond with the carbon atom. So, so here are the 9 alpha hydrogen atoms. So increases the stability of this carbocation basically by uh, using the hyperconjugation here. So in vacant p orbital, the electron are donated by the hydrogen atom basically. In case of the mesomeric effect basically, the mesomeric effect is basically like this. For example, here we are having OCH3 group, we are having any CH plus and CH3 basically. So here this electron of oxygen here donates its electron and it gives stability to this carbocation basically. So it is basically the mesomeric effect. And here the inductive effect is the distance dependent effect basically. After 3 to 4 carbon here, we does not see that of lot of change due to inductive effect as it is the distance dependent basically. And this mesomeric effect is also somewhat like distance dependent here. But in case of the resonance here, resonance is not the resonance is not the distance dependent basically. So here we can see the structure of phenol basically. So it is how, so here we can see double bond OH plus. So these are all the resonating structure basically. So so here phenol for the phenol we can draw these two types of the resonating structure. So this type of effect is called as the resonance basically. So it is the distance independent effect basically, the resonance. So here the position of the double bond has been changed here.
Yes. Yes, good. Next, move on coordination chemistry. Yes. But the main application of
Yes, yes,
coordination chemistry in inorganic and chemistry,
yes,
etc.
yes, yes. But here the coordination, 1 minute, sir.
Yes, carry on.
Sorry sir, some network
Okay, no problem.
issue
Yes.
was there. So basically, uh, basically the coordination compound has the lot of applications here basically. So for example, if you see about the cisplatin, which is used as the anti-cancer drug here. So basically, this is the cisplatin basically. So which is used as the anti-cancer drug, and another here the lot of metals basically which are not dissolved in the solution basically, which we dissolve with the help of we dissolve them by making their complexes in the solution basically. And another usefulness of the coordination chemistry is that here the two different uh, metals basically can be separated from the reaction mixture basically. If we are having the two different uh, metals that we can separate by using making making their coordination complexes here, and by separating these two coordination complexes, uh, we can separate them. And also the purification of the gold and the silver from their ore is also done by forming their complexes basically with the coordination compound, and we can separate and we can separate them. Also the various metals are separated from the reaction mixture by forming their precipitate basically. And after forming their precipitate, so this precipitate is basically the coordination complex only, and after that we separate our that metal basically. So like this the coordination compounds has the lot of advantages here. So the lot of coordination compounds are also used as the catalyst basically in the various reaction mechanism.
Yes. Yes. What the application of Werner theory?
Yes, so Werner, yes sir. So the Werner was basically the very first theory which was put forward to know about the structure of the coordination compounds basically. So so here the Werner basically told us that how the complex forms basically. He told here about the primary and the secondary valency basically. So for study the Werner has taken the complex which was basically CO COCl6 COCl6 6NH3 COCl3 CONH3 6Cl3 basically. So here basically the Werner tell us about the secondary valency basically. The secondary valency decides the coordination number of our complex, and the primary valency basically uh, secondary valency tells us about the coordination number of our complex, and the primary valency tells us about the oxidation state of our of the metal ion which is involved in the reaction basically. So here basically he has told that basically uh, he reacted this complex with AgNO3 basically. So when he reacted this complex with the AgNO3, so here he taken the 3AgNO3. So here he got CONH3 6 as it is, and 3AgCl basically. And in another case here he taken the complex that is NH3 5Cl3 with 3 AgNO3. So here he saw that only the 2 moles are required here, and here we got the NH3 5Cl or twice AgCl. So here he observed that the only 2 AgCl has been removed, and here the 3 AgCl has been removed. So here the secondary valency is shown by the solid wedge lines basically. So this valid 4 lines he show with the help of the solid lines, and this 3Cl he show with the help of this type of Cl basically. We call it as the primary valency, and as it is as the secondary valency basically. And also in case of this complex, basically, he shown that he, he explained this complex as this is the CO, and this NH3 is as our secondary valency. So he's shown this with the solid lines, basically 4 and 5. And here, as this Cl here, he's shown this with the solid line as well as the dashed line, basically. So he has said here that this Cl is is here explaining both the valencies, basically primary valency as well as the secondary valency. So and his explanation was also explained with the help of the molar conductivity, or the uh, as we know that here the amount, the compound that is formed here, basically is greater in case of this, as here we are having four charges here. So here the conductance will be higher in this case. So it was also supported with the help of the conductance as well as the crystoscopic measurement, which we called as the freezing point depression, basically. Yes, sir, that's all.
Yes. Any drawback of Werner theory?
Yes, yes. So the Werner theory was basically, the Werner theory was having a lot of drawbacks, basically. So here the Werner theory has told us that this Cl, basically I take one example here, that is CO, NH3, 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 1, 2, 3, 4, 5. So the Werner theory basically told us that the Cl molecule is basically responsible for maintaining both primary as well as the secondary valency. But this is not like that. The Cl is only determining the secondary valency. Means here it is the deciding the coordination number of our metal. And also the Werner theory was not able to tell about the structures, basically, of the compound, because the Werner theory has predicted the lot of structures which was basically the not right, basically. So the Werner theory only tells us about the coordination numbers, primary valency and secondary valency. It was not able to tell us the magnetic moment or the geometry, basically, or the hybridization. So this was the drawbacks of the Werner theory, basically.
Yes, good. Any uses of Werner theory in real life in our society?
Yes, yes, sir. Sir, matlab, any researcher proceeds with the smaller development in this field. Basically, the Werner theory was the very first theory which was developed, and after that, all these theories was developed by studying the Werner theory only. So every research goes by step, basically. So the Werner theory, the most contribution that I think that the Werner theory told us about the secondary valency, which decides the coordination number of our complex, and the ionization valency, which decides the oxidation state of our metal ion. So this was the major achievement of the Werner theory, that it was able to told us about the structure of the complex, basically. So how it forms, basically, the ionization pair and the non-ionization pair, basically. So the Werner theory basically told us that, for example, we are having this compound. So Werner theory told us that only these 3 Cl minus will dissociate. This complex will not dissociate in any case, basically. So this was the very first theory, basically, and it was able to tell us some of the uh, properties of the complex, basically.
Yes, good. Next, move on ligands. Yes, what the main application of ligands in coordination?
Yes. So ligands are basically the compounds which we call as the Lewis base, basically, which donates its electron into the vacant orbital of the metal, basically. So this metal are basically the Lewis acid here. So to form the stable complex with the metal, and basically there are the various types of ligands, like monodentate, bidentate, tridentate, pentadentate. Yes, sir. Like that.
Yes, good. What the application of IUPAC nomenclature? What the purpose of IUPAC in chemistry? Explain.
Yes, yes. Sir, IUPAC basically is a union, International Union of Pure and Applied Chemistry. So here, in case of the coordination compound, basically, so it was developed to name the coordination compound, because as the chemist in India and the chemist outside the of the India get confused with the same compound, because if this compound is having the common names, the common name can differ basically, but IUPAC name will help us because they will same everywhere in the world, and also the IUPAC name will give us some idea that how the structure of the complex will be there. So the IUPAC names were very important. Firstly, if we take the example of any complex basically, which is basically a CO, NH3, 6, Cl3 basically. So here basically the first rule is that we will name cation first. So here it will dissociate like this, 3 plus 3 Cl minus. So we will call it as a hexaamine. Hexaamine. So we will not change the cobalt here. We will simply write cobalt because it is in the cation basically. Hexaamine, cobalt, third chloride basically. So it is named like this. But if you are having metal ion in the anion basically, so if you are having any complex like this, CN6 3 minus and K3 suppose here. So here we will write the cation firstly. So here we can write as a potassium hexacyano cobaltate basically, because it is in the anion, it is present in the anion basically. So cobaltate, hexacyano cobaltate, and at the last we will write its oxidation state here. So in this type we give the IUPAC name to the coordination compounds.
Yes, good. Next is isomerase. What the difference between isomerase, organic and inorganic?
Yes, yes. Isomerism in basically, if you talk about the difference in inorganic and organic basically, so in organic basically we see the two types of isomerism, that is the geometrical and optical isomerism, the cis trans isomerism that we see in organic basically, and also the optical isomerism, that is we need the chiral center basically, the compounds which are mirror images of each other, that is the enantiomers, that shows the isomerism. So this type of isomerism normally we see in organic chemistry, and the isomerism that we see in the inorganic chemistry is basically the structural isomerism. Most of the structural isomerism, like the first one that we will talk is the ionization isomerism.
Yes.
Hydrate isomerization. The ligand isomerism. Complex isomerism. So this type of isomerism we naturally see in the inorganic compounds basically, but also that geometrical isomerism and the optical isomerism also seen in case of the inorganic compounds also. So organic and inorganic isomerism is somewhat same only, but only the structural isomerism has more application